All right. We are now talking about carboxylic acids right now, and that allows us to review a little bit just how acids and bases work in general. How do we know if something's a strong acid? And we are able to kind of qualitatively determine how strong an acid is based on the stability of its conjugate base. So we evaluate the stability of so how do we determine an acid strength? We evaluate the stability of the conjugate base, and we'll just call that the CB. So if we have a more stable conjugate base, that means that the acid was more willing to give up a proton. So a more stable conjugate base came from the stronger acid. The stronger acid. Remember, evaluating the acidity of something. The acidity means that it is, if it's more acidic, it's more willing to give up a proton. If it's more willing to give up a proton, it's more willing to give up that proton because it's generating something that is more stable. So if we had these two molecules here, we have an alcohol versus a carboxylic acid. How can we evaluate their relative acidity? So acids give up a proton. So if there was a base around, it could grab that proton. It's donating its electrons to that hydrogen. The oxygen takes its electrons back, so that would make the conjugate base that would look like this. Same thing over here for this carboxylic acid. The base would just grab the proton. That OH bond would break to generate our carboxylate conjugate base over here. So over here we have the conjugate bases. So now's the time for you to take a minute to yourself, say which of these conjugate bases is more stable, and not just which one's more stable, but why, right? We always want to be thinking about the why. So which one's more stable, this one or this one? Answer it, pause it, boop, you paused it, you're back. This one's more stable. Why was that? Hopefully you've already drawn a structure to demonstrate why this is more stable than that, because just telling me isn't enough. We have to be able to demonstrate it with our chemical structures. Why is this one more stable than that one? Resonance. It's conjugated. We want to have charges aren't very stable when they're on just one atom. They're going to be more stable if they are distributed over multiple atoms. And we can show that through resonance structures. Those electrons can move there to make a double bond. Those move up there. So that shows that our negative charge is delocalized across two oxygen atoms, whereas with this oxygen here, all of the electron density is just on a single oxygen atom. So this is the more stable conjugate base. So this was the stronger acid. Stronger acid. We should already have up in our brains pKa values that allow us to look at these more quantitatively. The pKa of an alcohol, and again, you guys should know these, is around 16. The pKa of a carboxylic acid is around 5-ish. So lower pKa, stronger acid. We can't just memorize the pKa's. We need to understand why as well. It's because that conjugate base is more stable. And why was that? Again, it's because the negative charge is delocalized. And the bullet point on this page of the notes that we're filling in, and again, this is page 3 of our note packet, says delocalization of charge is always stabilizing, except when anti-aromatic. So why was this more stable? Because that charge was delocalized. So we're going to be doing a lot of this chapter, reviewing our acid-base chemistry and bringing in the different things such as resonance or induction or different elements, thinking about pKa's, all of those things. So this is a good intro though. So hopefully this is kind of feels like review. It should kind of feel like review.